Okay, I'm going to share my camera. Document camera. See that. And okay. So what I was thinking when I said the thing about you missed something, it might have just been a computational error, is that you missed number 1. So I just wanted to make sure that this was one you needed to talk about, or could we move on to something? Could we move on to the next one?
Actually, we do, because I don't remember trapezoidal sum, so that's why I got
Okay.
it wrong.
Okay. So in general, let's see, put a little post-it note on here. So generally speaking, a trapezoidal sum is going to be made up of terms that look like this. You're going to have a delta x times the average of 2 y values. And then you're just going to continue adding up those widths times average y value. So that's width times average y value. You're going to continue adding those up until you get to the last interval. If delta x is the same or is consistent, we can write a more compact version of the formula. I can factor out the delta x, and I'm also going to factor out the division by 2 from the average. And what that's going to leave is that, so the y1 here is only going to appear once, but the second y value is going to appear twice because it's used in the area calculation for the first rectangle, but it's also going to show up here in the next term, right? Because in the next term, this is going to be, I'm going to call this delta x1, delta x2 times y2 plus y3 over 2. So you see that the y2 values shows up twice in the sum, and so that means when we factor things out, we can just combine like terms. We got 2 of them. So then it's going to be 2 times y3 plus that. It just keeps going, and then it's plus, let's say, 2 times y minus 1 plus yn. So the next to the last y value is still going to appear twice, but the very last y value, the nth data point, is going to only appear once. This formula only works if delta x is consistent, meaning it's the same for every trapezoid. So this is the formula I used here in number 1. Delta x is always 2 units. And then, so it's delta x divided by 2, 2 over 2. And now I'm just taking, okay, the first y value is 8, plus 2 times the second y value, 8.5, plus 2 times third y value, which is 9, plus the last y value. And then from there, it's just a matter of doing the computation. You get 1. It's often the case, though, that, again, multiple choice strategy, that if you look at the area and find an upper bound and a lower bound for it, you can either narrow the choices down to 2 or all the way down to 1. So in this case, if you put an upper bound up here at 9 and just find the area of that big rectangle, and you can, and then, well, we don't know what the y value is exactly at that point, so I'll just use 1 here at 8. It's going to be pretty close anyway. So the area of that big rectangle would be 6 times 9. The area of the smaller triangle, or smaller rectangle, would be 6 times 8. So we know our answer's got to be between 48 and 54. The only one that's between 48 and 54 is choice B, even without doing the trapezoidal computation. Okay. So got any questions, lingering questions about that one?
No, I'm good. Thank you.
Okay. So then let's look at number 2. Number 2 is going to be a frequently missed question because it involves both fundamental theorem of calculus and the chain rule. And most students often forget the chain rule. Notice that the upper limit of integration there is not x, it's x squared. So we have to treat this f of x here as a composed function. Think of f of x here as being g of x squared. Because the place you would so the x value here that's input, well, that's up here, it's being squared first. So when you want to find f prime of x, you're going to find the derivative of the outside function, the g prime of x squared, but then you've got to multiply times the derivative of the inside function, which would be 2x. But in this case, when you take the derivative of g of x here is the integral. So when you take the derivative of an integral, the derivative and the integral cancel. So this is our g prime of x squared. Notice that the t's been replaced with the x squared. But then we have to multiply times the derivative of the x squared. That's our 2x. So then when we multiply those two quantities together, we just get 2x in the numerator, and then 1 plus x to the fourth, because x squared squared is x to the fourth.
Okay. Yeah, I forgot to do the chain rule. That's my mistake.
Okay, so you chose, did you choose?
I chose C.
Okay, yeah, gotta multiply by that 2x. Okay, so the next question that you missed was all the way over at number 9. Okay, so when I see an integral like this that involves a rational function, right? Polynomial divided by polynomial. This is a constant 1 up here, but we still think about, yeah, that's polynomial with degree 0. There's a certain kind of things I go through in order and check. The first thing I'm going to try to do is, okay, does this fit one of my special memorized forms, right? Because there's a couple of those, like the inverse trig forms, like 1 over x squared plus 9. Well, that would be an inverse tangent form. You wouldn't have to do anything with it. And there's a few other memorized forms that could match up with rational expressions. Well, it doesn't match up nicely. So the next thing I'm going to do is try to factor it. Well, if you play around with it for a bit, you notice that it doesn't factor over integers. But then if you just calculate the discriminant, you can find that the discriminant's less than 0. So that actually means it doesn't factor at all. So can't factor it, because if we could factor it, we could use partial fraction decomposition. Okay, so last resort is completing the square. So completing the square involves adding that 9 and then subtracting that same 9. Why did I pick 9 here to add and then subtract?
Because is it a factor of 6? Like 3, which squared is 9.
Okay, but it does. So let's be careful. So it's generally going to be b divided by 2 squared. So in this case, the b is -6 divided by 2 squared. Okay, and so that is -3 squared, which is 9.
Oh, I remember it. Okay.
Yeah. So that's an algebra 2 skill, and it doesn't come up real often, but it is in fact in our curriculum here. Because what happens here, well, okay, so we have to add that 9, and because we added that 9, I now have a polynomial I can factor. It's x minus 3 quantity squared. It's always going to be x plus or minus the b over 2. Then we got to balance out that plus 9 with a minus 9. So 18 minus 9 is plus 9. So when we put that back together, we now have an integral that does match one of our memorized forms. We recognize this as an inverse tangent form. because we have a linear function squared plus a constant squared. The best way to do these is to just memorize this formula. That the integral of 1 over u squared plus a squared du is 1 over a times the inverse tangent of u over a. In our problem, u is x minus 3. And a, well, 9 is 3 squared, so a is 3. So we just use that formula. Yeah, that's as complicated. And then there's the corresponding formula for the inverse sign. Integral of 1 over the square root of a squared minus u squared is inverse sign of u over a plus c. So, so I'm assuming it was including the square here that got you hung up.
That, and also I don't have memorized the inverse trigonometric ones derivatives, so
Okay.
I don't ever memorize those.
So let's think about test taking strategies here. I've got the integral of a constant over a quadratic. That cannot be a natural log function, because in order for it to be anything involving the natural log of a quadratic, we would need a linear function here in the numerator. In order for us to, I can't get here without doing u substitution, and I don't have the du that I need in the integral. All right, so you can eliminate that one by recognizing there's no u substitution that's going to lead to that. And then looking at the other choices, we just got to, okay, can we eliminate the arc sine or the arctan option? If we could eliminate arctan, we know what our answer is. So what I'm looking at here is that an arc sine is always going to involve 1 over a square root. An arctan is always going to involve 1 over quadratic. So based upon the fact that we've got 1 over a quadratic here, we know it cannot be the arc sine. So at the very least, we've got it narrowed down to these two, even if we can't remember exactly how the formula goes.
Is cosine also square root?
Cosine is also a square root, but you're not expected to have that formula memorized, or you're not going to be expected to use it on the test.
Okay, so arc sine square root and then arctan quadratic.
Yeah.
Okay, that's helpful.
Okay. Shift our focus over to number 10. So again, we've got the integral of a rational function. Integral of a rational function. But what I noticed this time is that the degree of the numerator is greater than the degree of the denominator. When the degree of the numerator is greater than or equal to, so degree of the numerator is greater than or equal to the degree of the denominator, that tells you to do long division. Because there's no u substitution that's going to make this work unless we can break it down and get the degree of the numerator less than the degree. So degree of the numerator bigger than or equal to degree of the denominator, we need to do the long division. Okay, so I need to divide x plus 1 into x squared. So how comfortable are you with the long division algorithm?
I'm pretty comfortable. I've done it multiple times before, and I'm usually doing it well.
Okay, so did you recognize that you needed to do long division here?
Yes.
Okay, so then did you get the integrand of x minus 1 plus 1 over x plus 1?
Yes.
Okay, so then where was your error?
Wait, what did I put? Number 10 was C. The answer D. So +2, where's that +2 came from? I put, oh, I think I misclicked. Did I? Let me see.
It looks like you either had one of these two twos incorrect, and it was probably the -2 since you chose +2 plus natural log of 3.
Oh, yeah, that's it. Yeah, I see it.
Yeah, because you had to, so yeah, the antiderivative of the -1 was a -x, and so when you evaluated it 2, you get that -2.
Yeah.
Okay, so that one was just a calculation error.
Yes.
Okay. All righty then, number 11. Ooh, our
Yeah,
least
that
favorite.
one, I don't even think I'd try. I got freaked out by that one.
Yeah, these are kind of the scariest looking multiple choice questions. But let me give you some tips here. When we see a question like this, where they either give us a definite integral and then the answers are in terms of these limits of sums, limits as n goes to infinity of a sum, or vice versa. They give us something like this and the multiple choices are integrals. We know this is a question about the definition of that definite integral. It's actually quite challenging in a broad sense to pick out, okay, this must be the one and only way to write this, because there's actually multiple ways, right? There's multiple correct integrals that correspond to a limit of a Riemann sum, and there's multiple Riemann sums that correspond to each integral. But there are patterns that the exam follows. The first one is that the delta x is almost always the width of the interval between the limits of integration. So in this case, b and a are 7 and 3, so that width is 4. So our delta x has to be 4 over n. So we look at our multiple choices and we eliminate the two choices that have a delta x of 1 over. Well, I actually, I may have jumped ahead here for a second. In general, what these look like is if the integrand is f of x, this is going to be f of some formula for x sub k times an expression for delta x. So what we're trying to do is say, okay, which of these limits has the correct f of x and the correct delta x to match up with our integral. So the analysis I'm going through here now is saying, okay, I recognize that my f of x is x cubed. So that means I've got to figure out, okay, what x value is being, or what expression for x is being plugged into f. Well, I look at all of these formulas. Notice that the thing being cubed is 3 plus 4k over n. Well, that the formula for x of k, the sampled x value, is always the lower limit of integration plus our formula for delta x times k. So since the lower limit of integration is 3, we found that our delta x is 4 over n. This formula's got to be 3 plus 4k over n. So that means this x sub k here, the x sub k that's getting plugged into f of x must be the 3 plus 4k over n. Well, that actually doesn't eliminate, actually, yes, it does. That eliminates choice D, because it's 3 plus k over n, not 4k over n. So at that point, you've got it narrowed down to one option, so you know it's got to be B. Sometimes, last resort, you need to make sure that limits of integration match up given the choices you've made for delta x and x sub k. There's a more difficult version of this problem where it's one of those multiple select problems where there might be 3 Riemann sums, Roman numeral 1, Roman numeral 2, Roman 3, and they're asked you which of these represent the integral, and there may be more than one correct answer, because there can possibly be more than one way to choose delta x depending on how you've chosen delta x. So the last thing, you don't have to do it in this problem, but is check, make sure the limits of integration actually come out to 3 and 7. The lower limit of integration is the limit as n goes to infinity of the first sampled x value, so x sub 1. Well, x sub k, so we're thinking about this formula with k equals 1. So it's the limit as n goes to infinity of 3 plus our delta x, which is the 4 over n times 1. So that's 3 plus 4 over n. Well, as n goes to infinity, the 4 over n goes to 0, so that limit is 3. That's correct. B, also the limit as n goes to infinity of the last sampled x value. So the last sampled x value is x sub n, because notice that all the upper limits of integration there are upper limits of the sums are n. So the very last x value is always going to be x sub n. So the formula for x sub n, we just take the 3 plus delta x over k, or 3 plus k over n, but this time the k gets replaced with n. We're looking at n. Well, 4 over n over n is always just 4, no matter what n is, and so our is 3 plus 4 is 7. So this is method of last resort. If you can't narrow it down in any other way, you go check the limits of integration. It's a little harder, or it's a little bit more involved, but sometimes that's the only way you can do it. Okay, so I talked straight through that one without asking any questions or letting you ask questions. Let me pause there and see if there's anything you want to go back to and discuss a little further.
Yeah. So for the last resort, you said the k for A will be 1 because it's the first term.
So yeah, so to be more precise, it's the initial k. But notice that all 4 of these options start with k equals 1.
Okay.
Yeah. So it's So for A, it's x, the first sampled x value, so in this case that's k equals 1. And B is always the nth sampled x, or the last sampled x value, which is n.
And okay.
Yeah.
Okay. That makes sense.
Yeah, these are ones where you need to watch the clock. If you haven't solved it and it's been 2 minutes, move on. Or make an educated guess and move on, because they can be time consuming, kind of think through all the possible combinations of things. Typically the ones they actually go on the AP exam, if you don't get intimidated by the question, they don't put the hardest ones on there. So as long as you don't freak out, you can usually get it.
Okay.
All righty. Let's take a look at, all right, we got 3 in a row. 13, 14, 15. Okay. All right, so 13 is about comparing the size of a definite integral with the various approximation methods. So right hand, left hand, and trapezoid. They give us the information that the first derivative of f is positive and the second derivative of f is negative. So that means f is always increasing and concave down. So the curve looks something like this, right? It's increasing and concave down. Well, what that tells us, and let me draw a bigger version of that curve. What that tells us is that any left-hand sum, right, that left hand, the sampled x value there on the left, is going to be an under approximation because its curve is increased, function's increased. And it means any right-hand approximation is going to be an over approximation. So because f prime is greater than 0, f is increasing, which means the left-hand rectangle is always below and the right-hand rectangle is always going to be above. So in this case, we know that the right-hand method must be on the right, up at the top of the inequality, and the left-hand method must be at the bottom. So that narrows it down to C and D. Now we just got to figure out how the trapezoid and the integral compare. Now, in general, trapezoid is always going to be a better approximation on either the left or the right. In some rare cases, it's not, but it's really, really rare. So you generally can assume that the trapezoid approximation is going to be closer to the integral than either the left or the right. But you can't. That doesn't help you here because they're both right next to it. All right, so let's think about trapezoids now. Because it's concave down, if I were to draw the trapezoid approximation over the trapezoid area down here is going to be less than the area of the curve. So for concave down curves, trapezoids are always going to be under approximations. For concave up curves, which we do not have here, if you think about that, if you have a concave up curve, the trapezoid is going to have more area than the actual curve. But we're concave down, second derivative is negative, so that means my trapezoid is an under approximation, which now eliminates C because the trapezoid is bigger than the integral here, and so our answer must be D, trapezoid less than value.
Okay, so I think I just switched my left and right because I think I'm used to always thinking left is always an over approximation while right is always under. So I think in this problem I have to look at the concavity.
For left and right hand rectangles, it's not about concavity, it's about increasing or decreasing.
So is the trapezoid for concavity?
Yes, trapezoid is determined by concavity. Left and right's determined by increasing, decreasing.
Okay, yeah, that's helpful.
Okay.
Okay.
Now, this problem does not involve the midpoint rectangular method, but it's true that if the trapezoid method is an under approximation, midpoint is over. If trapezoid is over, midpoint is under. They always are on opposite sides of the integral. So if they had included midpoint in this problem, we know that the midpoint would have to get squeezed in here. It would be an upper bound because the trapezoid's lower bound, midpoint's got to be an upper bound, but it's going to be a better upper bound than the right hand method because that's always going to be true. Okay. It's less often that you see midpoint approximations in this type of question, but it does happen sometimes. So other questions or comments on that on 13?
No, I'm good.
Okay. Now 14, I want you to look closely at 14 before we talk about it, because this is a pretty straightforward definite integral problem. So let's see if you can look over my work there and see if you can find your error.
Oh, okay. Yeah, I think I subtracted, like instead of adding like 3/3, I think I subtracted, so I got like 5/3.
Okay.
My problems were looking right, so I just took a guess. I was like, what am I doing?
So you differentiate rather than anti.
Yeah, I have that habit. I'm noticing I keep doing that. I don't know why.
Yeah, sometimes that's just a matter of getting working too fast. So every time you see an integral, just pause and go, okay, integral, antiderivative. Just, run that through your head. Okay, well then let's move on to 15. 15, let's see here. They want the value of the integral from 0 to -2 of 5 times g of x, given some information about g of x. Well, I'm going to do one thing first, is I can just factor out the 5, right? So what we really need to know is the integral from 0 to -2 of g of x dx, and then we just multiply that by 5 and have our answer. However, these limits of integration are out of order. The smaller ones on top, or the lesser ones on top. So I flip them, -2 to 0, and then that makes the coefficient negative. Once we have them in the right order, it's going to be a lot easier for us to use the given information, because they told us the integral from -2 to 2 and the integral from 0 to 2. So if I subtract the interval from 0 to 2 away from the interval from -2 to 2, it's going to leave me with the integral from -2 to 0. Right? You think about it. You can think about it as a number line. if I know the value, from -2 to 2, and I know the value from 0 to 2, so this guy right here is the 8, this guy right here is the 3. Well, if I want to figure out the other part, it's going to be 8 minus 3. That's the additivity property for definite intervals, that consecutive intervals must add up combined. So that's what I did here. If I want to go from -2 to 0, that's the one we want. I take the negative from -2 to 2, that's the whole. Subtract the part I don't want, 0 to 2. So there's the -5 for flipping the limits of integration factor into 5 times the 8 minus 5, -5 is -25. So what tripped you up on that one?
I think it was the 5. Like, I knew my answer was gonna be negative because, like, I know since I flipped it, like from the -2 to 0, then my answer was gonna be negative, most likely. So, and I did get a negative number, but I think I multiplied my 5. Like, you factor it out, I think I kept it in, so which is why I got -4 instead of -25.
Okay, so you may have just multiplied it times the first integral, but not the second one.
Yeah.
So yeah, no, okay, -5 times the 8 is -40. So you would have just forgotten to subtract that second bit at all.
Yeah.
Okay.
But what did I do with the 3? I guess I guessed, or I guess I just forgot about the 3.
Yeah, these types of problems almost always involve multiple properties. So we use the constant multiple property, we use the flip the limits property, and then we use the additive property. We ended up using all three. So you kind of got to think carefully that, okay, what can I do and in what order can I do it to get down to my desired result? And generally, it's like solving an equation. You want to do things that involve multiplication and division first, and do things that involve addition and subtraction last, just like with solving an equation.
Okay.
All right. Then you got 16 correct. Then 17 and 18 we need to talk about. We got values of f prime, and f double prime at x equals 2 and x equals 6. And we're asked to evaluate the integral from 2 to 6 of x times f double prime of x. Well, because we have the product of functions here, and u substitution is not helpful. So anytime you see the product of functions or u substitution is not helpful, that means you should try integration by parts. Okay, the integral of a product of functions where u substitution is not helpful is probably going to be integration by parts. Notation wise, did your teacher use the u and dv notation?
Yes. Yeah,
Okay.
I did not think about that. Oops.
Okay. So when we're doing integration by parts, we need to pick the u and the dv first. Are you familiar with the acronym LIATE?
Yeah, it's logarithm, inverse. What was A? What is A again?
Algebraic.
Algebraic, yes, and then trigonometric, and then exponential.
Okay. So what does that acronym help you do? It helps you identify u. So in this, if you go from left to right, logarithm, is one of the functions a logarithm? No. Or either of the functions an inverse trig function? No. Are either the functions algebraic functions? Okay, yes. Every polynomial, linear function, square roots, anything that involves only algebraic operations is classified as algebraic. And so we do have a factor x that's algebraic, and so that's got to be u. And then everything else that's left over, the double prime of x are equal to b. If you know that u is x and you want to find du, you differentiate. So the derivative of u is du over dx, so that means d, which would be 1, so that means du has to be dx, just like in u substitution. If dv is f double prime times dx, we need to anti-differentiate to find v. We got to have all 4 of our parts, so we need to know what v is. All right, well, the antiderivative of f double prime of x dx is just f prime of x. All right, so now we got to put the pieces of the puzzle together. So let's write the formula down. So the integral of u dv is u times v minus the integral of v du. If it is a definite integral from a to b, you have to evaluate u times v on that interval, and then the integral has to be evaluated on that same interval. And that's the situation we have here. We have a definite integral. So u is our x. So u times v is u times f prime of x. V is f prime of x. Evaluated on the interval from 2 to 6, minus the integral from 2 to 6 of v du. V is f prime of x, du is dx. I usually delay this evaluation until the last step. So I've just grouped the whole thing together to be evaluated on the interval from 0 to 6. We've got negative f of x here because the integral of f prime of x is going to be f of x. All right, so then we're going to plug in 6 to this expression, plug in the 2 to the expression. Well, x is 6, and then we need to know what f prime of 6 is. Well, f prime of 6 is 2, minus f of x, so f of 6 is 3. Okay. So this is evaluation at the upper limit minus evaluation at the lower limit. Okay. So this time we're evaluating at x of 2. X of 2, prime of 2, prime of 2 is 4, minus f of 2, f of 2. So algebra or arithmetic, and you get 15. So I'm assuming from your original reaction, you just didn't recognize that this was that you needed to use integration by parts.
Yeah, I just didn't recognize that.
So that would explain. So this also kind of explains what's going on with 18.
Yeah,
so
exactly.
It's another integration by parts problem, but it's more computationally heavy because they didn't give us data. They didn't give us information in the table. We noticed it's well, in this case, it's indefinite. So we're easier because of that. So we've got 3x squared multiplied sine of x. It's a product of functions where u substitution is not helpful, which means it's almost certainly going to be integration by parts. Now, because it is a quadratic times a trig function, trig functions are periodic, they're repeating, and so are their derivatives, right? Sine is cosine, cosine is negative sine, negative sine is positive cosine, so on. Yeah, I said that wrong. But, it's cyclical. So when we have a function here, these derivatives are cyclical, what that means is that it's probably going to take more than one step of u substitution, or excuse me, integration by parts to get this done. We still use Liate to choose u equals 3x squared, the algebraic function. So that means dv's got to be the sine x dx. We differentiate to get u, we need to differentiate to get v. When we do that, we end up, when we use the formula, we end up with an interval here, 6x times cosine x. This is still not anti-differentiable using u sub or any other method. In fact, it's also a product function. substitution again on the integral 6x cosine x. So there's obvious choice, use 6x, d's got to be the cosine of x, differentiate, anti-differentiate, and then oh, I didn't finish right. Yeah. So then that would, so the minus integral of v to u is minus sine x times du is 6dx. Well, I didn't write out the final step here because I know what the integral of 6 sine x is. Okay, so we can, so if you go through, you can actually start eliminating multiple choices as you go through. You know it can't be A, that's just stupid, right? Because they just anti-differentiated each factor. Then C has the first correct term, and it has the second correct term. Oh, except that's minus when it should be plus. So that eliminates C. Actually, that also eliminates B because that says minus as well. And so that only leaves, even without doing that last step, we know our answer's got to be D. Because those two minus 6x rather than.
I knew it couldn't be A, but I just clicked A just to show you I really did not know this. So.
Okay. I want to show you something. When you have one of these where you have a product of functions where one of them is going to have cyclical derivatives, like a trig function, there's the tabular method that can make this work look a lot nicer, go a lot faster. I've got that written out back here on the back. So in our problem, we have the integral 3x squared sine x dx. We use Liate to choose u to be 3x squared, which means dv is the sine x dx. So what we do here is we make a little chart. The first line's always positive, and they alternate in sign as far down as we need to go. The u column, we differentiate. Derivative of 3x squared is 6x, derivative of 6x, 6, derivative of 6, 0. When we get that 0 there, we stop. And we anti-differentiate over here. The antiderivative of sine is negative cosine, antiderivative of negative cosine is sine, cosine. So what we do now is we now just put this thing together. Our answer is we just follow, we read across each row, except when we move from the u column to the v column, we got to drop down a level. So the first term is going to be negative. Oh, it's negative. All right, it's positive 3x squared times negative cosine x. So negative 3x squared cosine x. All right, then the next term is minus 6x times negative sine x. So negative times negative, that's term's positive. Plus 6x times sine x. Last term, plus 6 times the cosine of x. And then plus our constant. If we kept going here, let's say we got confused here and we said, okay, we're going to keep going. The next line here would be sine x, then that would be 0. Well, if you tried to do that, and we tried to add another term here, negative times 0 times negative sine x. Well, because you're multiplying by a 0, in that term and any later terms are always going to be 0. So that's why you know you're done when you hit that 0. There's a couple of other cases, special cases, I'll say, that with the tabular method, but polynomial times trig function is the most common one where this method will be useful, or anything times a trig function. Okay, so did your teacher show you this tabular method? And they may have written it down slightly different. Something you've seen before?
I didn't recognize that because I thought I was gonna be like the next unit. I didn't realize I'm gonna be this unit. So
okay.
Oh, a question.
Yeah.
Is the method like acceptable for FRQs, like showing your work?
Yes.
Yes.
Yes. You would need to. Yeah, it's acceptable. For anti-differentiation techniques, they really don't care about scratch work. and this would just be considered scratch work. As long as you had the answer here with all 3 correct terms and the plus C, you would get full credit. Because the rubric would probably be written, you know, like 1 point for getting the first term, and then maybe a point for getting the second and third term, and then, oh, you lose a point if you leave off the plus C. But there wouldn't be any points, you know, involved with actually doing the use substitution. It would be just associated with the answer. All right. We've got 5 minutes left. Let's, so we've got just enough time. We're not going to have time to look at the response, but you've got the rubrics, the solutions and rubrics to look at, and you did a lot better on those multiple choice, so I don't feel bad about taking a bit longer on the multiple choice today. So we've got the integral of another rational function. Notice that the degree of the numerator is equal to the degree of the denominator. So degree of the numerator is greater than or equal to degree of the denominator means we need to do long division. So, oh, here's where I did the long division, dividing the x squared plus x minus 2 into the 2x squared plus x minus 1, which you said you knew how to do that. So that long division results in quotient of 2 plus the remainder of 3 divided by the divisor, x squared plus x minus 2. This doesn't completely solve the problem. X squared plus x minus 2 can be factored. So we have a constant function over a linear function that can be factored. So now I use partial fraction decomposition on that constant over quadratic. Now, I don't think, you know, we have not talked about partial fraction decomposition. So if we have, say we've got 1 over, and I'm just going to use 1 for a simplicity. C and then x minus b. Let's say we've got a constant over a factored polynomial. That can always be decomposed as some constant a divided by x minus c plus some constant b divided by x minus d. And this is the only case that you're required to be able to do on the exam, which means we can use the shortcut method, the cover-up method. A is always going to be the value of 1 over x minus b evaluated at x equals c. So I'm taking the original polynomial here and covering up. In order to find a, I cover up x minus c, right? Cover it up, and evaluate the remaining expression at the root of x minus c, which in this case would be c. So that would be 1 over c minus d. B is going to be 1 over x minus c, evaluated at x equals d. Again, you're covering up the x minus d and then evaluating the remaining factor at the root, which is d. So that would be 1 over d minus c. Notice that these two things are the same, except they have opposite signs. Only thing that's different is the order of subtraction, so there's going to be the opposite signs. So in this case, a and b are always just going to be opposite numbers, right? So have the same absolute value. So does this, how are you with this generally, this partial fraction decomposition method?
I mean, I use that to try to solve it. I didn't do the long division because I didn't recognize. I also use it when the exponents equal each other. So I use it like I set it all equal to the numerator, which was a little like time consuming.
Yeah. There is a way to do partial fraction decomposition from the start, but it's really, really hard, as you found out.
I tried to do that. That's why I was.
All right, so it gets a lot easier if you recognize that you need to do long division first because the degrees are equal or numerator degree is greater than denominator. Definitely gives you an easier problem. Because from there, the antiderivatives are pretty simple, and then you just got to recognize how to combine those logarithms into the correct expression. But even if you didn't figure out how to combine those logs, just notice that it can't be a or c because they both have that constant of 2 in them. we know the antiderivative of 2 is got to be 2x. So that eliminates A and C. So even if we can't figure out the final answer, we know we're educated guessing between B and D. Well, and even from there, I think D's much more likely to be the answer because it's the log of those factors rather than the log of the quadratics. We know that the antiderivative of 3, a constant over x squared, not a quadratic, substitution doesn't work on that. So it's not just going to be a simple logarithm. You've got to decompose that first and then take the derivatives of each of the terms. All right, any final questions on 20 or any other problems that we've talked about?
No, I think I'm good. I think I asked all my questions.
Okay, cool. All right, so you've got access to the solutions in the rubric for the free response. Take a look at those on your own. If you get stuck on something, just shoot me an email and I'll help you clarify any of those solutions rubrics via email. All right, well, it's been good. I will post, I'll do the follow-up post probably tomorrow, and then I'll post the assignment for next Tuesday, either on Thursday or Friday.
Okay.
All right, you have a great day. I will see you next Tuesday.
All right, thank you.
Bye.